I got two big tricks to pull off here today. We're cheating. We're absolutely cheating with this part of statistics. I mean, I've told you before, statistics is crap. This is a big cheat that we're gonna do here. About this independent condition from checking your bins. Technically, if we sample without replacement, the probability of success changes from selection to selection. Technically. But here's the thing in statistics, when we go to take a sample of people from a population, we're not going to randomly choose somebody and then put them back in and randomly choose a second time so that they're independent. We're going to choose 50 people. That is sampling without replacement. That technically violates the independent condition. We'll see about that. Example, 14% of students are left-handed. If there are 25 students in this room and they're left-handed, find each probability if I select 2 students at random. Okay, the first one, I'm just going to go find the probability of picking one kid and they're left-handed. Picking one kid at left-handed is 3 out of 25, and 3 divided by 25 is 0.12. Okay, watch what I'm going to do here. I'm going to say with replacement, and I'm going to say without replacement. Okay, that without replacement is going to require us to use a conditional probability for the second one. If you're going with replacement, the probability of left-handed and left-handed would be 3 out of 25 times another 3 out of 25 because I put the one kid back in there. And so there's still 25 kids. So we get rid of this stuff. Oh, that's bad. That's bad. Never mind. Okay, there we go. 3 divided by 25. That's going to be 0.12, right? So I'm going to go 0.12 times 0.12. Let's just do it that way. I get 0.0144. If I'm replacing, the probability of picking 2 left-handed kids out of these 25 kids is 0.0144. Now let me show you what happens when the independence condition gets violated and I'm sampling without replacement. The probability of left-handed and left-handed is going to be different because they're no longer independent. I don't get to just multiply them together. So that technically, I'm going to write it down here. This one technically goes like this. It's the probability that you have a left-handed kid times the probability that you pick a left-handed kid given that you picked a left-handed kid. Right? That's how that went, conditional probabilities. So the first one is just the 3 over 25, but the second one would be 2 left out of 24, wouldn't it? That's what this would be, 2 out of 24. If you already pick a kid and the kid's left-handed, there's only 24 kids and there's only 2 of these kids left. So now let's see what happens when I go parentheses, 3 divided by 25, parentheses, and then I'll multiply that times 3 divided by 24. That's not right. That's not right. I can hear you guys yelling at me through the camera. 2 out of 24. Multiply that and I get 0.01. Now you guys, those are different, but how different are they really? You know what I mean? Like, is it a real big deal if it's not independent? I mean, do you know what I mean? Is it really that? Okay. They're very different. That's what I'm going to say. There's very, very different probabilities. Now, look at this scenario. There are approximately 1,350 students at Keeneland High School, 1,350. Let's assume there are exactly 14% of them. That's 189. Find each probability if I select 2 students at random. Okay, I'm going to find the probability that I pick one and they're left-handed. That would be 189 out of 1,350. 189 out of 1,350. Let's see, 189 divided by 1,350 is 0.14. Duh, of course it's 0.14. I already knew it. Okay. Anyway, let's find the probability that I pick. The first one is left-handed, and then I pick the second one that is left-handed, and I'm going to say this is with replacement. So this is an independent situation, and so this would be 189 out of 1,350 times another 189 out of 1,350 if I put the kid back in and I pick again. Okay, so isn't that basically 0.14 squared? 0.14 times 0.14, I didn't round it, it was 0.14, and so it's 0.0196. 0.0196. Now let's see what happens when I do this without replacement. I'm going somewhere, work with me here. The probability that's left-handed and left-handed, but this time without replacement is going to require that this second one is the probability that is left-handed given that the first one was left-handed. So we go, I gotta write this real small, sorry about this. 189 out of 1350, and then the second time there will only be 188 left-handed kids out of 1349 left in the pool. So here we go. Parentheses, 189 divided by 1350 times 188 divided by 1349. And let's see what I get. I get 0.01951. Okay, those are almost identical. As the number of trials gets bigger, the difference between here ends up being a lot smaller. Okay? And so this is significantly less different. So the exception to the independent condition I from the bins, we will consider trials in a binomial setting. I mean, they were kind of close anyways. But that could be different enough. I mean, that's half of a percentage off. If you're multiplying that times something, it could be significant enough to change things. This is not 0.5% off. You gotta go 4 decimal places before you see a difference here. They're pretty much the same. We'll consider trials in a binomial setting to still be independent because their probabilities are pretty much the same when we are sampling without replacement, so long as the number of trials is less than 10% of the population. So long as the number of trials is less than 10% of the population. What that means is you're not taking so many out of this population that it really has a big effect. See, up here, when we took one kid out of here and went from 25 to 24 kids, that's enough to make the probability be different from here to here, 24 to 25. But down here, 1349 versus 1350, that's such a big denominator, honestly, that like this isn't going to be a big deal. So how do we keep that denominator big enough so that it's not a big deal when it's sampling without replacement? Make sure your sample is less than 10% of the population. This, I'm going to say for us, this is going to be very important later. It's not going to make any sense to you right now. It's condition number 1. That is condition number 1 that we will use in a giant write-up starting in chapter 8. Okay, we just stumbled across a big deal to us. Let's go to the next page.